everyone. Today we'll be doing section 2.1 on arc length. We're getting to 8.2, which is on the surface area that revolves around like either the x-axis or y-axis. Back in chapter 6, we found the volume, and now we can calculate the surface area. So, well, let's derive this formula for arc length, which will involve an integral and integration. When you got an arc like this, I guess we could start with, well, there's the arc, we're trying to get the formula for the distance of it. But we can think of, let's start with just a straight line. Can we just use the distance formula to begin? So that's what we'll start with, just to derive this formula. And the distance between just 2 points, x1 and x2, is the square root of, I can just write it as change in x squared plus change in y squared, right? And we'll start there. But we're trying to get a formula that represents what? This length of this arc here. Well, we'll start with just the distance between 2 points, but that's straight line distance. So that's a good start. But then we're thinking, well, can't we just take this right here and break it up into a bunch of other segments, right? Just a bunch of segments, an infinite amount of segments. Set a limit towards infinity and sum up all those distances, right? And that's where we're going. So we can actually represent the length of that arc. So to do this, do you recall the mean value theorem for derivatives? I'll just put MVT. It said that the derivative of x had to equal some f of b minus f of a all over b minus a. You remember this with mean value theorem? There had to be some value c, and we could look at it even in this image to apply the mean value theorem. Does everyone agree at some point along this curve, the slope of a tangent line to the curve would be equal to that slope being parallel? Y'all agree? That's the mean value theorem. Well, we can use that to kind of get this whole integral derived. I'll call the b minus a just a change in x. I'll write this again. B minus a just be change in x values. And I can call this f of b minus f of a just a change in the y values, right? Can you isolate the change of y? And then we can substitute it in there. All right, let's do that. What would change in y equal? It'll be equal f prime of x times f, change in x. Well, what we're doing right now, we're just going to derive the formula. It's kind of neat. But I'm going to take this and put this right in there and substitute. All right. So now we're going somewhere. So what's this formula for the distance, which we're looking for eventually the arc length? What would this now equal? Getting closer. We'll leave the change in x squared, but what is this over here squared?
F prime of x delta x?
Yeah, f prime of x delta x all squared. F prime of x, make sure it's all in that parentheses there, delta x squared. And both of these have a delta x squared, don't they? So I can factor out a delta x squared. Well, first I'll put it right here. I'll factor it out right there. Delta x squared, what would be left in the parentheses? That would just be a 1, and then you'd still have this f prime of x all squared. I want to make sure the whole thing gets squared, so I'll put a big thing that around. And can't I take that outside the radical? What's the square root of delta x squared? And delta x is always going to be positive because we'll do b minus a where b is higher than that. So we don't have to put absolute value bars in. Pull it right out here. All right, so now we got some. This can represent the distance between the 2 points. Cool. But that's only distance of a straight line. Right? That's just what, from here to here? Here to here, here to here. That's just representing one of these infinitely small segments, true? we need an infinite sum, the limit as n approaches infinity. So to come up with the formula, I'll take this right here, all that right there. By the way, you can write that as dy dx if you want. And we're like, okay, this becomes the limit as n approaches infinity of the summation I equals 1 to n of all that right there, the square root of 1 plus f prime of x all squared. Hey, is everyone okay if I write that as dy dx? The f prime of x? The derivative of y with respect to x. Alright, dy dx. Plus all squared. And I have this what? Change. But now, what's that look like when we write it as an integral? This is just the integral from a to b. You recall change in x, that's just what?
dx.
Dx, all right. Put that there. And there's your formula. And the limit as n approaches infinity of all those. Get the length of that curve. Isn't that cool? There's the formula. You could put f prime of x here or dy dx. That will give us the length of any arc. Or if you think of any curve. The integral from a to b. Where a and b would be xi's, right? x1, x sub 2. Hey, by the way, similarly, we don't have to go through something like this again. But it could also equal this. 1 plus dx dy, derivative of some expression x in terms of y squared, and then this would be a dy. This would also be equal. You go, when would I want this? If you had a curve that was like, let's say x equals what? Maybe y squared or something. And then you go, oh, okay. So you take the derivative of x with respect to y. And what is the derivative of x with respect to y there? What would it just be? 2y? Right? Well, let's try one, everyone. We'll start with this nice formula right here. And we'll come back to this later. This is a nice lead-in into section 8.2. So these two sections, 8.1 and 8.2, we're doing today, they go together. But we now have a formula for the length of an arc. Pretty cool, though. All comes from the distance formula, which came from Pythagorean theorem. So cool. All right. So let's try one, everyone. The directions in the book, let me read it to you. They go, find the, an important word here, exact. All that means is you won't be able to use that math 9 function off the calculator, right? Or you can use it to check your decimal reading that you get off the calculator, but we're going to have to get the exact value. So find the exact value or the exact length of the curve. I'll use the same wording. Find the exact length of the curve. The curve is y equals 1 plus 8x to the 3 halves. How far we got to go? Let's go from x equals 0 to x equals 1. And you don't have to graph that curve right now, but let's find the length of that curve. From x equals 0 to x equals 1, the curve y equal to 1 plus 8x to the 3 halves. You agree we should use this? Right? We can get dy dx. We got x values, they gave us 2 x values. True? Does that make sense? I didn't want you to feel like you were wondering, why shouldn't I use this? They give us 2 x values here. We use that to get the length of the curve. Alright. Well, it looks like we're going to need a derivative. So before I write the integral, what is dy dx? Or f prime of x? What's the derivative of y with respect to x? Derivative of 1, 0. What's that derivative? Nice. 3 halves times 8. 24 over 2, you got 12, huh? Then you decrease that power by 1, and 3 halves minus 1 is 1 half. And we'll just put this in the formula. Keep in mind, you're going to square the 12 and the square root of x, right? All right. So let's set up. This would be the length of the arc. Arc length equals integral 0 to 1 square root 1 plus all that squared dx. But we'll simplify that first. 12 squared is what? 144. That's the square root of x, isn't it? X to the 1/2. X to the 1/2 squared is just a nice x. So all we have to do now is evaluate this. They said exact, so we're going to have to do the math, like one of these methods, substitution rule or integration by parts, partial fractions. Isn't that substitution rule though? And we're going to do a U sub on this. That's what we're going to use. We're going to let it do U sub. Here, I'll change the color. Here, let U equal to 1 plus 144x. So what's du? 144 dx. So what's the dx? Just 1 over 144 times the du, right? But now we can get this thing rolling. See, now we'll just have a square root of u. We can integrate that. Right. Replace the dx with 1 over 44 du. Okay, you're done. And then the square root of a u. This should be hard at all. I'm leaving this blank. Does anybody like to set the limits there? Just make sure they're u values, right? These were x values. That was x equals 0 to x equals 1. What would the u values be? From, what's 1 plus 144 times 0? 1, if you want to change these, what would be this number? What's 1 plus 144 times a 1? 145. But some of you do what I did previously in lessons where I just left them blank. Kept going, and I resubstitute and use the original 0 and 1. I wanted to show that because I do notice in grading your papers people like to change the limits. Not everyone, but some students like to do that. All right. What's the integral of u to the 1/2? That would be
2/3 to u to the 3/2.
outstanding. Outstanding. 2/3 u to 3/2. See, did u to 3/2 divide 3/2, which means multiply to 2/3. I'll just plug these numbers in. So what I'm doing now, everyone, I'm not putting my resubstitution of this because I'll use my just u values. I'll put that in there, and subtract them. I can reduce that a little bit, can't I? 2 isn't 144 what? 72 times. What's 72 times 3? At 216? Is that right? Alright, I'm just going to set up a parentheses. I'm going to substitute that number, subtraction, substitute that number. This is an irrational value. 145 to the 3/2. But this is neat. What's 1 to the 3/2? And so it's totally appropriate if you just want to leave your answer just like this. That's the length. The exact length of that curve. The exact length. The exact arc length. Which is kind of neat. All right, no more days of geometry where all we knew was what? 2 pi r. Of course, like just a sector. A little portion of the circle. We can do any curve we got now. So 8.1 is a neat jump in terms of mathematics. Anybody want to see how Bob writes this? Remember who Bob is? So we want to write it like Bob. Bob writes that as, right, 145, that's the square root of it, right? Cubed. So he thinks the square root of 145 times the square root of 145 times the square root of 145. So Bob will write this as 145 times the square root of 145 minus 1. Cool, so I'm going to give you that option. Which way do you like to write it on a test? Which way do you prefer? Is this fine with you? Just as nice as that, right? But that's, when you look in the back of the book, you're gonna see when they get that 3/2 power a lot of times. Like 5 to the 3/2 would be 5 square root of 5. Or 7 to the 3/2 would be 7 square root of 7. But it's okay to leave it as 7 3/2. I would have simplified this if it was a nice rational number. Like I'm thinking 4 to the 3. Oh, if I had 4 to the 3/2, I can simplify that. What's the square root of 4? 2. What's 2 cubed? 8. Okay, that's nice. Right? Rational, neat, nice integer, but that's irrational. Just gonna have to leave it like that. Any questions on that? Okay, cool. Let's try one more. I want to go to the end, buried down near the end where they said, find the length of the arc, and they give 2 points. All right, well, here's the curve this time. Hey, if you're wondering, that problem I just did, it was like number 7. Well, this one's like number 19. Out of section 8.1, y equals 1/2 x squared. Well, that doesn't seem like it'll be too complicated. Y equals, we can use this again. The 2 points, okay, I'm gonna pick different points than I saw in the book. How about 0, 0, 2? Find the length from there to the next point. How about at x equal to 2? I don't even know. Can you figure that out? What would be the y value? Just plug it in there.
2.
2. Oh, thanks. So we're going to find the length of that parabola. So we can find the actual length of that parabola from the point 0, 0 to 2, 2. Almost like a portion of the, you see a cable on the side of like the Bay Bridge. It has that parabolic representation. We're going to find the length from there to there. Okay. Well, these are x values right here. That's an x, that's an x, that's a y, that's a y. But we can go ahead and roll with this. Go from x equals 0 to x equals 2. Square root of 1 plus, what goes here though? Not f of x, but f prime of x. And that derivative is not hard.
Should be x.
Yeah, 2 times a half is just 1x, right? So let me write this again. So this problem's interesting. It's like we get to there. Like now what? It only take a little while to do this, everyone, but can we talk, because we can really update some old topics we've done in this course. It's like, man, how the heck we can integrate that?
Can we use one of the identities for the triangle?
Brilliant. He recognized this as one of those trig substitutions. Armando, way to go. And it was the 1 plus x. Remember that was the tan? So I'm just going to draw, to attack this problem, and we're like, okay, that's one of those trig substitutions. I'm going to draw a triangle. All right. I'll put theta here. I'm going to put x here. So I can do tangent theta is, right? X over 1. You all agree? X equals tangent theta. What would this be then by Pythagorean theorem? X squared plus 1 squared, take the square root. Right, by Pythagorean theorem? So we should be able to do this. This is one of those trig substitutions. All right, let's go substitute. What can I let dx equal? So we're updating an old topic, everyone, by doing this interval. This is a trig substitution. What's the derivative of tangent theta?
Secant squared theta.
Secant squared theta. So I can replace that dx with secant squared theta. What about this thing? Yeah, let's see. What would we replace the 1 plus x squared? All right. When we do all this side work, and then we'll go substitute all this stuff. That'd be 1 plus tangent squared theta, which is secant squared theta.
Yeah.
And the square root of secant squared theta is
Secant theta.
secant theta. I keep the absolute value bars, but I can remove those absolute value bars. Where is secant positive? By all students take crap. The first quadrant and
Quadrant 1,
And the fourth quadrant, right? I'll take this off. All right, this is just secant theta. But fine for where we just said, you know, in that first and fourth quadrant. All right. So what happens to this? This becomes, so cut there. This becomes, and I apologize, I should put my d theta there, right? I apologize for that. So secant times secant squared is what?
Secant cubed.
I'm just looking at this thinking, and good golly, we did a lot of work. I like doing this because we're updating that whole topic, but now we're here. So looking for something simple like what? Something emerged like just a cosine theta, right? But that's okay, we'll deal with this. We will definitely deal with this secant cube. Believe it or not, when you think of all the methods to get that thing going, like I can make what, a secant squared and a secant and all that stuff. But all the techniques we tried, it's like another trig substitution wouldn't work here. We just got to go to one of our methods right now. U sub, that's not going to work. Because u would equal secant theta, nothing's going to fly, right? The derivative is secant tangent. I don't see a tangent there. But how about this? Let's give this a shot. We're trying to integrate secant cubed theta. Let's try integration by parts. So when I'm going to go in here, I'll just change colors. We're going to try integration by parts here. Off this integral. Let's let u equal something, and let's let dv equal something. And we're going to apply integration by parts, where the integration of u dv equals what? uv minus the integral of voodoo. So how about let's just let the u equal secant theta. Because I'm thinking if we let dv equal secant squared, isn't that an easy antiderivative? That was my reason. I'm like, hey, we'll just do integration by parts. I'll let u be the secant theta, I'll let dv be the secant squared theta d theta. In terms of breaking up the secant cubed. Cool? What's that integral? That's an easy one. What's the integral of secant squared theta?
Tan theta.
Tan theta. Wait, good. What's that derivative? The u equals
Secant theta, tan theta.
secant theta tan theta. We'll leave one more room there. Du equals secant theta tan theta d theta. So we got secant theta, tan theta, d theta. dv was secant squared theta, tan theta. And I'm going to write this out. You got enough room right here. U v minus integral du. All right, what do we get? Secant theta times, what's v? Tan theta. Minus the integral of, what's v?
Tan theta
Tan theta
times secant theta, tan theta, d theta.
times secant theta, tan theta, d theta. I know this problem is funny because we get to here, it's like, man, it makes us try to lose patience. Now, we're almost there at the end. We're almost done. But it was funny, it started out like, it didn't look like it was going to be too bad. Boy, we've gone a ways, we're getting closer though. We're getting closer. Yeah, I'm going to rewrite this. What is it?
Tan squared theta.
Secant theta, tan theta, minus the integral of tan squared theta times a
Secant theta, d theta.
secant theta d theta. Hey, at least that's better than that. So I'll write this again. Secant theta, tan theta, minus. It's an identity I can use for tan squared. Secant squared theta minus 1, that should do it. That should do it. All right, secant theta, tan theta, minus the integral of, what if I distribute that? Secant cubed theta minus And before we get all flustered and get all upset, like this thing just seems like it's getting more complicated. Because what just reemerged?
Secant cube.
Before we think like we've gone in a big circle, we're actually a step away from getting this interval. I just want to make sure, I didn't want to rush on this. So far, so good. Once I did integration by parts, Kate, I liked your advice, make tan squared secant squared theta minus 1. But now I'm back to another integral of a what? Secant cube. Well, check this out. Here, I'll erase this part so you can see this. What was all this equal to? This. So I'm going to put this again. The integral of secant cube theta d theta is equal to this. And watch, someone in this class is going to spot something. Minus the integral of this. I'm telling you, someone's going to see it. Minus that integral. So before you just give up on this problem. This is never going. This is going nowhere. We've done a big circle, secant cubed emerged again. Anybody have an idea? Do you all see it?
It's plus.
Oh, right there, that's minus the plus. Thank you so much. Everyone's trying to distribute that minus right there, right? Minus all what? All that. And everyone's saying, hey, make that a plus. Well, let me just step away from that before it looks crazy. Do you see something on the left side and the right side that's identical?
Just add the secant 3 theta.
You bet. So this thing looks crazy, but this emerged again. And I can add it to this left side. How many of these would you have, like terms? Add it over here. How many secant cubes would you have? 2 of these.